From Canada's Perimeter Institute for Theoretical Physics, welcome to Perimeter Explorations. Classroom videos that investigate the frontiers of science. Join host and physicist Damien Pope of Perimeter's outreach team and leading researchers as they take you on an educational journey of wonder and discovery.
In observatories across the world, physicists young and old are mesmerized by the size and complexity of the universe. Before 1967, physicists thought they had a pretty good idea about what the universe was made of. But that year, physicist Vera Rubin looked at the stars in the outer regions of the Andromeda galaxy and observed something she didn't expect. The billions of stars in Andromeda orbit the center of their galaxy, much like planets orbit the sun. This was no surprise to Rubin. She also knew that planets in our solar system orbited more slowly the farther they were from the sun. So she expected the speeds of stars in Andromeda to decrease in a similar way, the farther the stars were from the center of the galaxy. But that's not what she saw. The speeds of the stars remained constant, no matter how far out in the galaxy she looked. What Rubin saw wasn't just slightly different from what she expected, it was dramatically different. The speeds were far higher than anticipated. Why were the stars in Andromeda moving so fast? Was the same thing occurring in other galaxies? Little did Rubin know that her observations would trigger a rethinking of what the entire universe is made of. It's easy to measure the mass of everyday items. A juice carton, a loaf of bread, an apple. But how do you measure the mass of something much, much larger, like the sun? To determine the sun's mass, let's use an approach we'll call the orbital method. We can calculate the mass of the sun by measuring the orbital speed and radius of one of the planets, such as Jupiter. Jupiter orbits the sun at 13 kilometers per second. The shape of Jupiter's orbit is essentially circular, with a radius of 780 million kilometers. So how can we use these two numbers to calculate the sun's mass? Let's start with Newton's second law of motion, which says that the net force acting on Jupiter is equal to its mass times its acceleration. The net force is the gravitational force the sun exerts on Jupiter. The magnitude of this force is equal to the universal gravitational constant times the mass of Jupiter times the mass of the sun divided by the square of the radius of Jupiter's orbit. Because Jupiter moves around the sun in uniform circular motion, we know that its acceleration is directed toward the sun and is equal to its speed squared divided by the radius. So if we substitute the gravitational force and Jupiter's acceleration into Newton's second law, we get the following formula. If we want to know the mass of the Sun, we rearrange the formula. This formula shows there's a relationship between mass and orbital speed. When we substitute in the speed and radius of Jupiter's orbit, we can complete our calculation of the Sun's mass. So what does this number really mean? Only that the Sun is 1,000 times the mass of Jupiter and 300,000 times the mass of Earth. Now that we know how to calculate the mass of the Sun, let's see if we can calculate the masses of entire galaxies. A galaxy is a vast collection of stars, typically around 100 billion. In many galaxies, gravity makes stars orbit the centre of their galaxy, just like Jupiter orbits the Sun. Because of this, we can use the orbital method to find the mass of a galaxy within the radius of the orbit of any star we choose. To do this, we need to know the speed of the star and the radius of its orbit. Ever hear of the Doppler effect? It's what happens when an ambulance rushes past you and the sound you hear changes frequency. As it approaches you, the sound shifts to a higher frequency. As it moves away, it shifts to a lower frequency. When you measure the shift in frequency, you can determine the speed of the ambulance. It's the same with light. If a star is moving towards us, the light shifts to higher frequencies, closer to the blue end of the spectrum. If the star is moving away, the light shifts to lower frequencies, closer to the red end. Since galaxies are really far away, we can't simply measure the speeds of stars by calculating distance over time. So the Doppler effect can be used to indirectly determine their speeds. The greater the shift in frequency, the faster the speed. Let's use the Doppler effect to help measure the mass of a nearby galaxy called Triangulum, which, like Andromeda, has stars orbiting at speeds higher than expected. Let's pick a star in the outer regions that's orbiting the centre of the galaxy with a radius of 400 million billion kilometres. It turns out that the star in the outer regions of Triangulum is orbiting at 123 kilometers per second. Let's substitute those values for speed and radius into the galaxy mass formula. This huge number is equal to the mass of 46 billion suns. 46 billion suns. That's pretty bright. Let's use that brightness to confirm the mass of the galaxy. To start, we'll need a flashlight. If we know the mass of one flashlight, and its brightness, we can figure out the mass of a whole wall of identical flashlights. How? By measuring its total brightness. Let's call it the brightness method. It's another way to measure the mass of objects in outer space. It also helps us understand why Vera Rubin saw the stars in Andromeda moving so much faster than anyone expected. Once you've got the total brightness, compare it to the brightness of the single flashlight. The relationship between the brightness of all the flashlights and just one will tell you how many flashlights there are. Then, multiply the number of flashlights by the mass of one flashlight, and you've got the total mass. We can use the brightness method to calculate the mass of the stars in a distant galaxy within a given radius. But there are a couple of problems. First, some galaxies are farther away than others. For example, Triangulum is farther away than Andromeda. Galaxies that are more distant appear less bright. even though they tend to emit the same amount of light as closer galaxies. But scientists know that, just like the brightness of a flashlight, the brightness of a galaxy decreases in a predictable way, based on distance. When a galaxy, or a flashlight, is farther away than another one, it only appears less bright. So scientists can determine the actual brightness of a galaxy if they know how far away it is. The second problem is that, unlike these flashlights, not all stars are identical. Fortunately, there's a relationship between a star's brightness and its mass that helps account for the different types of stars found in galaxies. Having solved the problem of unequal distance and accounted for different types of stars, physicists determined through the brightness method that the mass of Triangulum within a radius of 400 million billion kilometers equals 7 billion suns. But the orbital method gave us a mass of 46 billion suns. That's a difference of 39 billion suns worth of mass. Similar mass differences have been observed in over 1,000 galaxies. Something very, very strange is going on. But what? The brightness method assumes that all mass in a galaxy emits light, but the orbital method doesn't assume that. In fact, most of the mass in Triangulum measured by this method is unseen mass that emits no light. And because there's a relationship between mass and orbital speed, it's this extra mass that can explain the high speeds in Triangulum and in all other galaxies scientists have checked. Such as Andromeda, where via Rubin observed orbital speeds far higher than expected. Most physicists are confident that Andromeda, like Triangulum, is dominated by unseen mass, and they think that this additional mass is responsible for the speed she saw. By looking at satellite galaxies and other distant objects, physicists now think that, in most galaxies, this unseen mass extends much farther than the outermost stars. In this image, we represent this mass by the pale blue shape. Because the unseen mass doesn't emit or reflect any light, it's known as dark matter. The speeds of stars and galaxies aren't the only evidence for the existence of dark matter. Albert Einstein's theory of relativity strengthens the case. His theory says that just as a lens bends light, a large mass in outer space, such as a cluster of galaxies, bends light travelling near it. This is known as gravitational lensing. The bending affects the light reaching us, distorting the image we see of whatever lies beyond the mass. The good news is that lensing occurs whether we can see the mass or not. That means we can detect dark matter within a cluster of galaxies from the distortion it creates in the images we see of more distant galaxies. This is a cluster of galaxies called Abell 2218. The thin arcs are actually images of galaxies far beyond this cluster. Each of these images is showing distortion, dominated by huge amounts of dark matter within 2218. Gravitational lensing lets physicists map out detailed distributions of dark matter in vast regions of outer space. In this image, entire galaxies appear as individual white spots, dark matter as pale blue shapes. Putting together what we've learned from the orbital, brightness, and lensing methods, there's strong evidence for the existence of vast amounts of dark matter within galaxies, as well as between them. But knowing the dark matter takes up vast portions of the universe still doesn't tell us what dark matter is. Maybe dark matter is made up of planets. They're hard to detect because they only reflect light. Maybe we've failed to see a lot of planets in distant galaxies. The Sun makes up 99.9% of all mass in our solar system. That leaves only 0.1% of the total mass for all the planets, asteroids and comets in the solar system. This means that if dark matter were made up of planets, there'd have to be thousands of planets the size of Jupiter for every single star in every galaxy in the universe. But our solar system has only 8 planets, not thousands, so it seems very unlikely that planets account for all of dark matter. Another possibility is that dark matter is made up of brown dwarf stars. They're bigger than planets, up to 10% of the mass of the Sun. And they're also hard to detect because they don't shine. Black holes may be another possibility. They have so much mass that even light can't escape from them, making them a likely candidate. These two possibilities can be checked out because we can detect brown dwarf stars and many black holes using gravitational lensing on a smaller scale. Instead of looking at distortions in galaxy images within clusters, scientists measure the temporary brightening of individual stars brought about by gravitational lensing. Using this technique, we can account for some dark matter, but not all of it. There's also another way physicists can estimate how much of dark matter is made up of black holes. The explosions that take place when they're created spew out readily detectable heavy elements. From the amount found, they can estimate the total mass of black holes in the universe. These calculations indicate that black holes only account for a small fraction of dark matter. Having ruled out planets, dwarf stars and black holes as making up the bulk of dark matter, scientists looked at a number of other ideas that also failed to deliver. So what other possibilities could be considered?
Maybe we got the picture completely wrong about the universe, and we should be open-minded.
Some physicists think there is no dark matter.
Either there is something we haven't seen, some dark matter or whatever, or the theory of gravity is wrong. So people who work on modified gravity attempt to explain anomalous behavior in the universe, modifying Einstein's theory of gravity.
These scientists think the orbital method can't be used accurately on something as large as a galaxy.
I think dark matter really has holes in it. And it's possible that these alternative theories of gravity could correct those holes.
They think that when it comes to galaxies, Newton's law of universal gravitation needs to be modified.
Every time something doesn't work in the sky, you basically either say our theory of gravity is wrong, or it's just there's something out there we can't see.
Changing the laws of physics is a pretty radical step. But it wouldn't be the first time it's been done. Still, any new law of gravity would have to be rigorously tested before it's accepted. Most physicists are confident that our current ideas about gravity are indeed valid for something as large as a galaxy.
For me, it's almost certainly not modifications of gravity and not ordinary matter, like planets or black holes.
Maybe there's some new kind of matter there, or maybe we don't quite understand how things are working. This is always an option for everything.
The preponderance of the evidence is certainly pushing us towards dark matter.
I would say that probably probability that this dark matter exists is close to 100%.
But what makes it compelling is that there's many lines of independent evidence that point in the same place. And in that sense, it's like the evidence for atoms 100 years ago, that what convinced people that atoms existed was not any one line of evidence, but that you had many lines of evidence that all converged on the same conclusion. And dark matter is like that.
So all the evidence for dark matter is circumstantial, if you like, but there are 4 pieces of circumstantial evidence all pointing the same way. So this has got to be looked at.
These researchers think that the bulk of dark matter is made up of a new type of subatomic particle, one that's completely different from the protons, neutrons and electrons that make up everything on Earth. Many physicists think that hypothetical subatomic particles known as weakly interacting massive particles, or WIMPs, make up the bulk of dark matter. WIMPs were initially proposed because they don't interact with light, the fundamental characteristic of dark matter.
A new kind of particle it seems to just nail it in all the places you see it. And so that, for me, is the convincing thing. So my money is on some new kind of particle.
Axions might also make up the bulk of dark matter. They're very light, having much less mass than even electrons.
It doesn't look likely that axions really could be responsible for this kind of things, because right now experimentally left only very, very small window where axions could work. Also, it's not so natural prediction of the particle physics.
When you run them through simulation, just putting something like a WIMP in the simulation, you generate structure that does very well when you compare it to galaxy rotation curves and the behavior of clusters and the large-scale structure.
Whether or not the bulk of dark matter is made up of axions or WIMPs, most physicists think that on average, 90% of the mass of every single galaxy in the universe is dark matter.
Knowing that 90% of what's out there is something completely unknown, understanding what that is almost certainly going to change our picture of how nature works in a fundamental way.
Nothing of the physics we know right now can explain it. So there's this real, manifest evidence, like this huge sign in the universe that says, look, there is new physics beyond what we know.
It's a very big open window, and that's how physics work. We always have open questions, and by resolving them, by understanding them, we go a step further, a step deeper.
The universe is like a city at night viewed from a plane. The stars are like city lights, and dark matter is everything else you can't see. So when physicists look at the night sky with even the most powerful telescope, they're only ever seeing a tiny fraction of what's out there. Dark matter isn't just found in distant galaxies. Our Sun, along with the rest of the solar system, is orbiting the center of the Milky Way galaxy. Like all other galaxies, our own seems to be full of dark matter. And so, dark matter particles should be streaming onto the surface of our planet. In fact, if dark matter is made of WIMPs, then millions of unseen particles are passing through your body every second. Over the last few years, physicists have been conducting a variety of experiments to find out if either WIMPs or axions make up the bulk of dark matter. It's been very challenging, since these two particles rarely interact with anything else directly. Occasionally, a WIMP should collide with the nucleus of an atom, triggering a faint vibration. Physicists have set up a number of highly sensitive experiments to detect such vibrations. Unfortunately, cosmic rays from outer space can also trigger the same sort of vibration.
Right now, there are 50 cosmic rays on surface going through your brain every second.
Because Earth blocks most of these rays, many dark matter detectors are located deep underground.
So what we do is we get underground in Snow Lab, 6,800 feet below ground, where the cosmic ray signal is hugely reduced, and it's a much better environment for doing an experiment for a rare event like a dark matter scatter-off.
At Snow Lab in Ontario, Canada, several dark matter experiments are in development.
The main challenge, and it's not only for us, but for all dark matter search experiments, the direct search experiments, is the backgrounds. The backgrounds are particles that we know of, that they are around us, but we don't want them close to our detectors. So basically, we have to shield our detectors from these particles.
One team of researchers hopes to detect WIMPs within a superheated liquid.
We have a gel with millions and millions of small droplets of a freon inside. So when there is an interaction of a particle inside of these droplets, this interaction might put enough energy for this phenomenon to happen inside the droplet. So you have an explosion. So the droplet that's liquid becomes a gas bubble. And we can hear this explosion using acoustic sensors.
Experiments looking for WIMPs are underway all over the world. In the United States, Europe, Japan, and even at the South Pole. So far, none of the experiments has detected a dark matter particle. No physicist has been able to determine if WIMPs, axions, or something totally unexpected is the answer.
Well, science is ultimately about the data, isn't it? And the data will either show dark matter or it won't.
It is a good thing that we really have all these alternatives and that it's in the hands of the observers and of the experimentalists.
Yeah, it's exciting. It's very exciting. It means there's really something there we don't understand yet.
We do not know precisely what is it, but we know what it cannot be.
I think dark matter right now is the best candidate to explain what's going on.
I think within the next few years, we'll have definitely a much better understanding of what's going on. And I really hope within the 10 next years, we'll be able to point down on something.
It's a real opportunity for physics. I mean, it's not just explaining one missing thing in the universe. It's really, once we understand what dark matter actually is, we'll have understood a completely new direction of physics. There's no question.
We've come a long way since Vera Rubin first observed discrepancies in the orbital speeds of stars in Andromeda. But we still have a long way to go. Years after her observations changed our understanding of what makes up the universe, Vera Rubin said, "The sky will not be the limit." And she's right. Physicists will continue to look to the skies and beyond until the mystery of dark matter is solved.